Hey guys, welcome back to another A-Level Maths Made Easy video. This time we're looking at parametric differentiation. I think in the last video I said that it was differential equations, which this leads on to differential equations, but it isn't. So we have parametric, then implicit, then we have the differential equations. And the reason why I put it in this order is not just because it's the order in the book, which it is, but also because this builds up the skills that we need in order to solve differential equations. So just so you're aware of the kind of order, we've done the chain rule. We're going to do parametric differentiation, which uses the chain rule. Then there's going to be differential equations, not next video, but the video afterwards. As usual with the normal stuff, most people that watch these videos aren't subscribed, so if you would consider subscribing, that would be amazing. And in the description there is a link to my website and to my email where you can book tuition lessons, or you can ask me any questions that you may need. But let's get into how we differentiate parametric equations. Now, there are two ways to do this. The first way is to create the Cartesian equation, where you have y equals and then something to do with x. So for example, in this case, I would literally just sub in t into here. So you could have square root x equals t, which means which means y is equal to 3 square root x, and then differentiate that. That is one valid way to do it. But I'm going to show you another way to do it using the chain rule, and the reason for that is, as you know from when we did parametric equations, some of them can get quite tedious, where you have to use sine squared plus cos squared equals 1, for example, or you may need to do some other funky business, which is very tricky to then differentiate. In fact, if you have the ones where it's sine squared plus cos squared equals 1, you have to use implicit differentiation, which we haven't done yet, in order to solve them, in order to differentiate them. So while that is a valid method, it's not something that's going to work for all parametric equations, or at least it's not going to be viable for most of them. So you can do it, but it might take you a really, really long time. So this way works, but can be very long. So if you prefer to try and figure out the Cartesian equation and then differentiate, you're more than welcome to. That is a valid method. But again, remember, you might need to use implicit differentiation, which kind of sucks. The second way is using the chain rule, which is the main way I'm going to show today. If you want to practice using the Cartesian form, I'd recommend just going back to my video on parametric equations, where I show you how to get the Cartesian form, and then you can just differentiate that, which is nice and easy. So, here's how it works. As we know, we are looking for dy by dx. And then what I'm going to do is I'm going to look at what we have and look at what we can find out. Because we have x equals t squared, we could find out dx by dt. And, well, it's 2t, right? And because we have y equals 3t, we could also work out dy by dt. So I need to use, because of the chain rule, I need to use these two things to try and work out dy by dx. So if I start with the dy by dt, I'm completely fine with having a dy on top. In fact, that's what I want. I want dy in the numerator. But I want to get rid of the dt in the denominator. So that means I would times it by dt over something. Well, the only other expression I have is for dt by dx. Now, the eagle-eyed among you may see that this is dx by dt, it's not dt by dx. So instead, in order to find dt by dx, we're going to take the reciprocal of both sides, which means we're going to flip both sides. And remember, this is 2t over 1, so it becomes 1 over 2t. So that means our answer here is dy by dt, which is 3, times 1 over 2t. So in other words, it's 3 over 2t. And that's the answer for dy by dx. Now, some of you might not be too happy with that because of the fact that I've taken the reciprocal. So the other way to look at it is like this. We have dy by dx. We could say that's the same as dy by dt divided by dx by dt. But remember, when you divide fractions, it's keep, flip, change, right? So that's where we get the dy by dt times dt by dx. However, if we use just this, we do get the same thing, where we get dy by dt, which is 3, divided by dx by dt, which is 2t. So either way you do it, it's the same thing. Personally, I prefer this because it links better to differential equations, which we come on to next. Well, again, the next part of this series, I guess. And that's more useful in real life as well. So being able to do this is a lot better than being able to just kind of flip things around like that. So again, I would recommend doing it this way and kind of figuring out what you have and what you need and then working it out. In my opinion, that is a far, far, far better way to do it. So let's use another example. Again, here is where we'd have to use sine squared plus cos squared equals 1. But if you notice, we actually have numbers, right? And it'll make it very messy. So instead, what I would prefer to do is just do what I did before, which is differentiate both sides. So this is going to just change to cos, so it's going to be 2 cos t. That's nice and easy. And dy by dt is going to become negative 6 sine t. And again, we want dy by dx, so let's think about what we have and what we need. Well, dy by dt seems obvious. And again, I want to get rid of the dt, so I want to times by something with dt in the numerator. And I want dx on the bottom instead, so it's going to be dt by dx, which again is the same as doing dy by dt divided by dx by dt, but I prefer this way. In order to find dt by dx, which is, we're going to use this, and we're going to take the reciprocal of both sides. So we're going to flip both sides. So that's dt by dx equals 1 over 2 cos t. So now we have dy by dt, which is minus 6 sine t, multiplied by 1 over 2 cos t. So that gives me minus 6, and there's 1 over 2, so that becomes minus 3. Minus 3 sine t over cos t. So if you wanted to simplify that further, that's minus 3 tan t for our dy by dx. And again, these are 3 or 4 mark questions, and I don't think so far it's too spectacular. It's not too crazy, hopefully. So again, with something like this, finding the Cartesian equation, again, it's possible because it has to be possible, but it's extremely, extremely difficult. So here, I would say in an A-level maths exam, I would say for most A-level students, it's not possible or would be exceedingly difficult to find the Cartesian form of this equation. So again, we're going to have to use the parametric method, which I've been showing you. And as you can tell, we're going to be using the chain rule. So don't forget, this is the same as having sine t squared, and this is the same as having cos t cubed. So remember how we do that? We bring the power forward, so that becomes 2. We differentiate what's inside the bracket, so instead of sine t, it's going to be cos t. And then we times it by the bracket with a power that's 1 less. So in this case, it's going to be times by sine t by itself. Technically to the power of 1, but I'm not going to put to the power of 1 because I'm not crazy. And yeah, that would be that for dx by dt. For dy by dt, it's a bit more exciting. So again, we bring the power forward. We differentiate what's on the inside, so instead of cos t, it's going to be negative sine t. So negative sine t. And then we times it by the bracket with 1 less power. So that's going to be cos. Yeah, I'm going to write cos squared t. So if I simplify both of these just to make my life a little bit less painful, I'm going to write sine before cos. I'm not actually sure why, but in a lot of kind of maths literature that I've read, they do tend to put sine before cos. I should probably figure out why, but let's just do that. As long as it's consistent, I don't really care. The reason I want it to be consistent is so I can clearly see if things cancel out. Again, with dy by dx, how do you want to work that out? Well, again, we have dy by dt. And there's a reason why I'm explaining this every single time I do it. It's because when we get onto differential equations, I know I keep hyping up this topic, but you're going to get given a bunch of different things. It could be the rate of change of surface area of a cup. It could be the flow rate of a liquid through a hose pipe. It could be anything. You aren't going to get things where it's, oh, it's always divide this. It's always times this. No. It can be anything. It could be the rate of change of a radius or something like that. So you need to think in your head and make it really explicit why you're doing what you're doing. That's how you learn. And not just that, is if when you say it, you think, hang on a minute, that doesn't make sense, then you can correct it. When I'm teaching, a lot of the times I speak what I say, as you guys know from the videos, which is better for understanding for you guys, but it also helps me. Because if I say something, I think, wait a minute, that didn't make any sense. I know I've done something wrong, which is really, really key. So again, what would I times by? Well, I want to cancel out the dt because I have dx on the denominator, so I have to have dt in the numerator, right? It's the only way it can cancel. And because I want dx in the denominator, I must have a dx in the denominator here. So dy by dt is negative 6 sine t, so I mean, that's just, you can read it, cos squared t, and it's multiplied by 1 over all of this. So that's going to be 2 sine t cos t. And now we're going to get our black pen of destruction, and we're just going to cancel stuff out. So I can tell that sine t is going to be on top, so it's going to cancel with the one on the bottom. One of the cos t's is going to cancel with one of the cos t's on the bottom, and the 6 and the 2 is going to cancel to 3. So this literally just becomes negative 3 cos t, and that is it. Just double checking, making sure all of that makes sense. Yeah, because 6 divided by 2 is 3. Hang on a minute, what happened here? See? Not exactly sure why I did that. So that means that was always a 3, which means this is still going to be over 2. So I'm going to get rid of that there and change that to a 3. And like I said, see, everyone... I'm going to leave that in because that's a really good learning point. Again, look through your work, talk through it, see if it makes sense. I'm not exactly sure. I must have thought that the squared was like a normal 2 or something. Or maybe I looked over here. Either way, weird. And the rest of it is correct though. Minus 3 cos t over 2. So yeah, let's get on to 2 more. One of them is going to be an exam question. That's going to be the last one. Remember that when I do these videos, these aren't meant to give you the hardest possible questions. They're meant to give you a selection of all of the most common types. Now, I am planning on doing some videos closer to exam time where I go through questions that my tuition kids and even my students at school have sent me over like holidays and stuff to go through, because some of them are really, really tricky and require a bit more thought. I know that sounds a bit pedantic, but I think those questions would be really good to go through because they kind of highlight the thought processes you need to get those A's and A stars in A-level maths. So I'll definitely do those close to the time. But these questions here are meant to give you a really good spread and a good understanding of how to do the topic. The problem solving will come in another video, unless the topic is just problem solving, like differential equations is. And so let's get straight on to this actual exam question that came up. So a curve has parametric equations, blah and blah. Show that dy by dx is a half tan 2t. Any of you that have gone through past papers yet, which I assume you have if you're this far into the course, you know that they love their show that questions. That way you can do part B if you haven't done part A, or you can get part A correct. So we have x is sine 2t, so I'm just going to straight away say dx by dt then is, remember what you do, you differentiate the inside, bring it to the front, so that'd be 2 cos 2t. And dy by dt, well, you bring the power forward, so it's 2. You differentiate, so it's cos. And then there would also be a sine t, yep, because it'd be to the power of 1 now. And all we need to do is work out what the dy by dx is, which again, we've had a lot of practice doing. Now this is, actually, this question's a pretty good one to do, just because I can tell already, if we look at this, we have cos t sine t and we have cos 2t. Getting to tan 2t, it's a bit, it might take a bit of get going, but this just shows how linked together all of the topics are in maths, because we're definitely going to have to use some kind of double angle formula or something like that. So if we, actually I'll do it on the next line down, we have 2 cos t sine t. I've already spotted it, hopefully you guys have. 1 over 2 cos 2t. So what's really nice here is we can actually cancel out, unlike in the last part. And we get, do we want to do that? No, I don't want to do that yet. Let's not do that. Because there's a reason why we're not going to do that yet. So, why did I undo what I just did? Well, the first thing is that there is actually a half in the answer. So that 2 in the denominator must stay, but the 2 in the numerator goes away somehow. So I need to think about how that works. The 2 here has to go away without cancelling with this 2. And I know that because the answer is a half. The next thing I know is that the answer has tan 2t, and at the moment I don't have tan 2t. Let's write out what tan 2t would look like. It would be sine 2t over cos 2t. Now if I want to be even more specific, because of the half here, this would be sine 2t over cos 2t. Now the denominator is perfect, but the numerator is not correct yet. But if you actually have a look at it, that is indeed sine 2t. Because if you think about what sine 2t is, again, if you use the addition formula, the reason why I'm going to use the addition formula here is because remember what I said, I don't like memorizing things. It's just not worth it, in my opinion. So instead, use the addition formulas, which you get given in your actual exam. You get given on the formula sheet. And you get sine t cos t plus sine t cos t. And you get 2 sine t cos t, which is exactly what we have here. It's just I wrote cos t sine t. So that equals 2, no it doesn't. That equals sine 2t over 2 cos 2t, which is a half tan 2t, which is exactly what they want. And so for part B, find an equation for the tangent to the curve at the point where t equals pi over 6. So remember, if it's a tangent, it means it has the same gradient, so same grad. And remember, when you're working out an equation of a tangent, and this works, bear in mind, equations of tangents have come up in a lot of topics, all the way since year 10. So this is quite a familiar topic, hopefully. You need, y equals mx plus c. You need a gradient, and you need a coordinate. And we actually get given everything we need. We have the equation for the gradient, and we have a coordinate that not really a coordinate, but we have the parameter that we can sub in to find the coordinates, because we can say x equals sine 2 times pi over 6, y equals sine squared pi over 6, get our coordinate, and we can sub that into the dy by dx in order to get the gradient. So let's do that first. M would equal, I'm happy with writing this, half tan 2 times pi over 6. Now, because t is in terms of pi, it means we're definitely putting it into the radians mode instead of degrees. That's just the logical thing to do. So, in your calculator, it's not menu, it's not that button either. Shift, menu, angle input, radians, let's go. Tan 2 pi over 6. God, I had a geriatric moment there for a second. Root 3 over 2. And that means the gradient of our line is also root 3 over 2. So we actually have m already. How nice. Now, to find the coordinate, all we're going to do is we're going to sub in pi over 6 into the original x and y. So x equals sine 2 times pi over 6. And y equals, I think it was sine squared. And it was just x, wasn't it? Sorry, t. Yeah, pi over 6. So let's work those two out. We have sine 2. God, I did it again. Jesus Christ. 6. And we get root. You know what? I should have guessed that from. Actually, no. You know what? I'm gonna give myself a pass there. Then here we're gonna delete this. I'm going to put this in brackets, I'm going to square it, and we get a quarter. Wonderful. So our coordinate that we're subbing in is root 3 over 2, and a quarter, which is going to give me a disgusting number, but, that's the way the cookie crumbles, I guess. Y equals root 3 over 2, x plus c. Sub in your value for x, sub in your value for y, so we get a quarter equals root 3 over 2. Actually, this isn't going to be as bad as I thought, because those root 3 over 2 is going to become something nice. A quarter equals 3/4 plus c. So subtract that over, that means that's negative a half equals c. So y equals root 3 over 2x minus a half. Yeah? Yep. Yeah. Did it say in any kind of form? Nope. So we're all good. Yeah, we're perfect. And yeah, that's all there is to it, to be honest. Once you practice this, it is kind of the same thing over and over again. Again, when it comes to problem solving questions, Stuff like this doesn't have much in the way of problem solving. It's mainly just equations and a process that you have to be able to do. So practicing that is of course very important. But when we get onto, and again I keep saying this, the differential equations, that's where it starts to get more problem solving. And of course we have a lot of stats and mechanics that have a ton of problem solving in there as well. But hopefully this kind of gives you a bit more confidence and gives you a good foundation if you're reading ahead. It doesn't really get much trickier than this. The only tricky part is actually doing the differentiation, but it's the same process over and over again. So hopefully that makes you feel a bit more confident. But other than that, I will see you in the next one.